So today, as Dan was saying, we're going to start talking about what do you want me to? Is my shirt messed up? Oh, thank you. It's on camera. I don't want to. Yeah. Okay. So last week we talked a lot about foundational stuff, the foundational theory. We talked about some applied things in terms of like large-scale GWASs, and I think that a lot of the things we did last week are not necessarily things that all of you are going to be involved in because it's you have to come up with this large scale, gathering a consortium. I think this week we're going to be focusing a lot more on kind of where the rubber hits the road, things that are you'll be easily able to apply to your own research, and so we're excited to talk about these topics, and hopefully this is stuff that's going to be really useful and applicable to you all. So first we want to talk about this idea of Snip Heritability. So as you recall, from last week, this is the additive model that we were discussing, so the true causal model. So remember that we have we're saying that there are J variants in the genome, and so X are the variants, and we're saying that there's this beta, which is kind of the true effect size, the true effect of that variant, and we said there's this thought experiment of this, we can think of this beta as what we would get if we were to switch in a variant at conception. And so we said this is nice, it's also the best linear predictor. So we drew these connections between what we think about the causal model is, and also what we would get if we were to estimate this in a best linear predictor. And then we talked about heritability. Specifically, there's this idea of narrow sense heritability, which is the variance of the additive factor, this linear part here, divided by the total variance. So this is kind of just remind you about all the things we talked about last week. One of the concerns that we have when we're making our polygenic scores is that we don't measure every single variant. And so we maybe just have a subset of them. A lot of times we're just restricted to, for example, common variants that show up in at least 1% of the population, or a lot of genotyping arrays don't actually genotype every single SNP. And so we just have a subset of the J. And so I'm gonna index all of these J SNPs. I'm gonna say the first K are the K that we observe. My clicker is not being very responsive. Okay, so here we are. Skipped a slide. Okay, so now I'm going to define this term that I'm going to call the additive genetic factor of Snips. And so what I'm going to do is I'm going to take the first K SNPs, the things that we observe, and I'm going to have a best linear predictor of the outcome with just these K SNPs. So now notice that this B here, I used to be using beta, and now I'm using B. So why is it? This is so crazy. Do you have your clicker? This one's, yeah, mine's being a little moody. So I said before, when we had the betas, that was a best linear predictor. And we have a best linear predictor here too. Why did I change the notation there? What's the difference between this B here and the betas that we had before? Do you think we could just use the betas? Like if I just said, okay, we're going to use the betas, we're going to be missing something. Any thoughts on what it is that we're missing?
So these ones are estimated and the other ones are the true?
Now, so in this case, these are also the true ones. So before we had we had all of the variants, and now we just have the subset. So now the problem's going to be that, let's say that we had a variant and it was perfectly correlated with something that's in our set of genotyped SNPs. But then, so we have two SNPs. One of them is genotyped, one is not genotyped. And then we drop one of so we drop the ungenotyped one. What's going to happen to that coefficient of the one that we have genotyped? Yeah, it's going to capture the variation from there too. And so we think of this as omitted variable bias, I guess. And so in that sense, these betas aren't the causal betas anymore, because the causal betas are these betas once we control for all variants at once. But in this case, these are they're still the best linear predictors, but we can think of them as capturing some of the variation, even though we've omitted a bunch of SNPs. We are capturing some of that variation because of LD with the omitted variants. Okay, so now instead of instead of saying narrow sense heritability, we can talk about we'll often talk about the Snip heritability. And so when we say Snip heritability, we mean how much variation is explained by just the set of genotype SNPs relative to the total variation in the phenotype. And so, we have this claim here that the Snip heritability is always going to be less than the heritability of all SNPs. So why is that? I just told you guys that these Bs are capturing the variation of omitted SNPs, but this is still going to be less. Why will this be less? Yeah.
So, it would only not be less if they were perfectly correlated with all the omitted SNPs.
Yeah. So if we could explain all of the variation of the omitted SNPs, then this would be equal. So I guess this should probably be less than or equal to technically, but in general, the Snip heritability is going to be less than the heritability, the narrow sense heritability. Okay. There's lots of ways that we can estimate Snip heritability. We talked about one of them last week, LD score regression. We're going to talk about one of the others this afternoon, called Gremel. And when we have the Snip heritability, we're going to go into more detail here, but we can think of it as an upper bound of how much our polygenic scores are ultimately going to explain. And it's going to be a lower bound on the narrow sense heritability. So this is just, the claim again. It's going to be a lower bound on what we could get out of all SNPs if we just thought about if we genotyped everything. But when we make our polygenic scores, upper bound on the total predictive power of the SNPs identified by the GWAS. Oh, this is not quite the same point. So what I meant here is that if we take the subset of SNPs that are just the genome-wide significant hits, this is going to be less than what I called the Snip heritability, because it's maybe just my computer that's going slow. Because this here is all genotype SNPs, and if we just took the set of SNPs that were identified by the GWAS, then that's even a further subset of that. If we had every single SNP, then as we've been saying before, we would approach narrow sense heritability, because but that's what we've defined as the narrow sense heritability. It's the variation explained by everything. So just as an overview, as I said before, there's kind of two main ways that you can get Snip heritability. One of them is Gremel. And the idea behind Gremel is we take a set of unrelated individuals, and we can measure how similar they are genetically. And if people who are similar genetically are also similar phenotypically, then that trait's going to be more highly heritable. We'd say that it's likely to be more heritable. Linkage disequilibrium's LD score regression compares SNPs. And so it says if two SNPs are related due to LD, and we see that when a SNP is related to lots of other SNPs, it explains more of the variation, then we say that's more heritable. And so we can see that we're getting at Snip heritability in slightly different directions. We're using some shared assumptions, but some different assumptions. But we can use these two estimates to sort of triangulate and see if they're consistent with one another. They should be approximately the same thing. So then how does, what is Snip heritability? Well, for a few phenotypes that we're interested in, how big do we see it is? So like for height, height is generally one of the more heritable traits. The Snip heritability of height seems to be about 50%. For BMI and education, we're at about 20%. Subjective well-being was measured 9% in this PNAS paper, although in some samples it's a lot less than that, depending on how well it's measured. Age at first birth, we're at 15. So as you can see, these numbers are still kind of substantial, but they're not as large as the numbers that we were reporting for the twin studies. Why not? Why are these going to be smaller than the twin study heritabilities? Yeah. This is just the same point that I'm making like 9 times. So hopefully you'll understand this by the end. So there's maybe 2 reasons though. So one of them is that the twin studies are aiming to get this narrow sense, the narrow sense heritability. So the heritability explained by a linear combination of factors. And so there might be a lot of SNPs that aren't well tagged. So they're not correlated with the SNPs in our genotype set. The narrow sense heritability from twin studies may also be overestimates. So if there actually is a lot of non-additive variation, like dominance or epistasis is the gene-gene interactions, then we might actually, we'll end up with estimates of narrow sense heritability that are too large. And so it may be some combination of both of these things. Okay, so that's the background that we need to talk about what heritability is and what we're looking at when we're making polygenic scores. So let's talk about what we mean when we say polygenic score. So I've heard, I think that we've been throwing around this term a lot. So let's be really concrete. So if we start with our additive model, so this is the additive factor just from Snips, which we said is this linear combination of genotypes. So when I say true polygenic score, what I mean is just this term here. And so if we knew what the betas were, and we had people's genotypes, we could calculate what a person's actual true genetic score was, right? And then the variance explained by this term, just we've defined the Snip heritability as the variance explained by the additive factor, and so the variance explained by the true polygenic score is going to be the Snip heritability. So we're good. When I say polygenic score, the problem is we don't know what the betas are, and we have to estimate them. And so if I say the polygenic score, I'm going to substitute in estimates for these weights and take this linear combination using these estimates. Now the problem with this is that the polygenic score is going to be a noisy measure of what we're considering the true polygenic score. And this is going to lead to our scores not being as predictive as the Snip heritability would imply there. And this is pretty easy to see. So if we have our beta hats, and let's say that we have some unbiased estimator of, or not B, like B hats. Let's say we have some unbiased estimator of these B's, and so they're equal to true B plus some noise. And so this means that our score, our polygenic score, is going to be x times these estimated weights. And we're going to substitute in true weight plus the noise here. And so what we're left with is the polygenic score is equal to the true polygenic score plus this mean zero error. So this is going to be a classical attenuation bias setting. So our score is going to be less predictive of the outcome of interest, and as a result, the R squared, if we were to take our polygenic score and regress it on the outcome, we're going to get something that is strictly less than the narrow sense heritability. If we had an infinite sample and we could estimate these weights in an infinitely large sample, then this error here is going to go to 0, and we're going to end up with just the true score. And so as we get large sample sizes, we should think that we're going to cap out at the true Snip heritability. And if we had an infinitely large sample and we were measuring every single variant, then our polygenic score, the variation explained by the polygenic score should eventually reach the narrow sense heritability. Okay. So one of the reasons that we really like these polygenic scores is because it's combining information across a bunch of different SNPs. We're going to have a lot more power for these polygenic scores than we would for just for one SNP at a time. And so here's the same table that I showed you before, but I've added this column here showing you what the predictive power of the polygenic score is based on this sample. And so the Snip heritability of height is 50%, and our polygenic score explains just 14%, right? BMI, the upper bound is going to be 20%, but we're just at 7. The first EA paper in a small sample explained 2% of the variation, but as we expanded the sample, it grew to 7. This is at 11% now with 750,000. So you can see this same pattern here. So let's think again about let's think about our board game friend. Okay, so our board game friend comes up and says, okay, you told me that I need really large power to do a GWAS of people who love board games. However, someone else did this big study on people who love board games, and I created this polygenic score, and because polygenic scores are more powerful, now I don't need to worry about doing power calculations, right? What should you tell your friend? You always need to do power calculations. That's what you should tell your friend. And then maybe slap him. So it is true that we're in a lot better position to with these polygenic scores, but we need to be careful that, this is not solving everything. We should make sure that the score we're using is going to be well-powered for the question that we want to ask. To get a sense of what well-powered might be for a polygenic score, if your R-squared of your polygenic score is like 7%, so this was what we had in the score based on just the EA2 results. I don't know what's happening with this projector. It's like a second behind me. OK, then we're going to have 80% power to detect it in a sample size of just 100 people. If we go up to 9%, then we will be well powered even with 85 individuals. And so this is getting to the size that we can start managing. We could use it in these small data sets that we're interested in to detect the main effect. We're going to talk about G by E later, and we'll need to do a slightly different calculation in that case. But if you wanted to do something in experiments or the HRS or some of these other samples, these polygenic scores seem to be a really promising way forward. OK, great. So so far, what I've been saying is that we're just going to use these betas, and we maybe have these b hats, but we don't actually have the b hats. What we have are b GWAS. Oh, that's not the point I wanted to make yet. Sorry. Oh no, this is. Sorry, I've not. OK, yeah, this is. OK, we have b GWAS. So what's the difference between b GWAS and the b's that we've been talking about? So how do we first? I guess the first question is, so when we're doing a GWAS, what does that come from? What kind of regression does a GWAS coefficient come from? Do we remember? Yeah, the GWAS are summary statistics, but if I told you this is a coefficient from a GWAS, that means we did a regression. What was that regression? Let's say I said, here's the GWAS coefficient for Snip 7. Yeah, it's an OLS for just one SNP. All right, so it's a simple, and maybe some controls. So why is that going to be different than the B's that we were talking about before? Yeah, it's the marginal effect, which means that not only is it going to capture, so before I said that these B's don't capture the SNPs that are ungenotyped. In this case, this is not going to capture any other SNP at all. And so as a result, the GWAS B is going to have information about every single SNP nearby. And so if we try to make a polygenic score and we use the GWAS B, then we're going to be double counting a lot of information. Say that we've genotyped 2 SNPs that are highly correlated, and we use GWAS B for the weight for this guy and GWAS B for the weight for this guy. This guy is saying, well, it contains information about this one over here, and so it's using the B that accounts for that information. And this one here contains information about the effect of this SNP over here, and so it's using the B that accounts for that information. And now they're both counting each other's information. And so we're gonna be double counting and triple or however many SNPs are in LD with each other. And so we don't want to use the GWAS betas directly as the weights. We want to do some sort of correction for the correlation or the linkage disequilibrium between SNPs. So if we had individual level data, we could just run, instead of doing one SNP at a time, we could run a bunch of regressions where we regress the outcome on our SNP and then just control for every SNP that's in LD. And so that would remove this double counting problem because we've controlled for the things that we observe. In general, we don't have individual level data. All we have are these GWAS summary statistics. So there's been a bunch of methods that have been developed to deal with the problem that all we have are the summary stats. And so kind of the first people who were introducing these types of things were doing something called pruning. And so what they did in that case is they took their GWAS summary statistics, and they would just pick some subset of them that were uncorrelated with each other, and they would make a score just based on those. So now there's not any double counting, because if there's 2 SNPs that are correlated, we're saying, okay, well let's just get rid of one of them. So why might that be a wasteful approach? What are we losing when we do pruning?
The effect of the SNPs in LD, because you're not capturing all the effect of the neighboring SNP.
Exactly, exactly. Let's say that we had two SNPs and they're correlated just like at 0.2 or something like that. So they're a little bit correlated, and we don't want to double count. So we say, let's get rid of this one. These are correlated. We hate you. But there's still a lot of information in this guy over here that we're losing. And so in general, these scores that are based on just pruning, a pruned set of SNPs, are going to be a lot less predictive than one that instead corrects for the overlap. So then there's a method that came out in 2012, conditional joint analysis. And what they notice is we know what the relationship is between the GWAS coefficients and these true B's that we've been talking about before. And it's just going to be a relationship of LD. So why can't we just use that information and try to get these B's? And that's what they do. So the relationship between B GWAS and the B's that we want, we're just going to left multiply by the LD matrix. So it's just the matrix of correlations between the SNPs. And so because that's true, we can just invert D and put it onto this side. And so you can get the true B's by just left multiplying by the inverse of the LD matrix. And that will fix that problem. And so that seems to be a nice trick. It turns out that a slightly more a trick that's going to be even better than that is if we go, in general, these Bayesian methods tend to have slightly more predictive power. And so LD-Pred was then developed in 2015, which does kind of Bayesian, but then it's a more Bayesian, kind of like Kojo, but it's a more Bayesian approach, and in general, these tend to be more predictive. And so I'm going to talk just super briefly about what LD-Pred, oh, yeah?
Sorry, Patrick. I kind of missed what these three solutions are.
OK, yeah. So the idea is that we have double counting. So the GWAS coefficients contain information about not only the effect of themselves, but the effect of everything that they're correlated with. Right? And so in this case, we just throw away the things that are correlated with it. In these two cases, we're going to try to just correct the coefficients for that correlation. And this is a kind of a more frequentist correction. This is going to be a Bayesian correction. Yeah?
So you were saying that the Snip inheritability is if I was to include the whole genome, right?
If you were to, so Snip heritability is if you include all of the genotype SNPs.
All the genotypes.
Yes.
Okay.
So narrow sense heritability is if you include every variant in an additive model. Snip heritability is just the heritability, the variation explained by the SNPs.
By what you actually observe.
By what you observe. And so what's a little bit fuzzy about that too is SNP heritability is going to change depending on what SNPs you observe.
Because I thought we were observing about 2 million and still we don't have those samples, so that's why I was confused a little bit.
Yeah. So we do observe a lot, but there's a lot of rare variants that we don't observe. Other structural variants and stuff would be included in narrow sense in principle, and we don't tend to observe those. I mean, all of those things will be tagged to some degree by the SNPs that we have on our GWAS chip, these common things, but not always. And often these narrow, it's actually really hard to tag rare variants using common variants.
Okay, no, I was
So-
just since you showed the H2 SNP and the R2 on the polygenic score, I wasn't sure if you were including everything in the other one. We just said we couldn't do it, so that's why I was.
Yeah.
Hey Patrick, sorry, I have another quick question. So, do you know how much difference it makes in practice to control for LD versus not to? I mean,
So
I
ISO's gonna-
remember in the initial Purcell paper, I think they did it both ways, and it really didn't make much difference at all.
I think it can make a lot of difference. So ISO is going to, it really depends on the setting. ISO is going to talk more about that. My sense is you can get an additional 10% on your predictive power by doing things like LD-Pred. Okay, so what is LD-Pred? So I think LD-Pred just conceptually is a simple-ish thing, but it's technically kind of hard. And so when we do LD-Pred, what we want to know is what's the expected value of all of these B's that I talked about, conditional on what we observe the GWAS coefficients to be and what the correlation structure is between our SNPs. And so, it seems like it's a pretty simple thing. We just want to know what do we think this is given that, right? And so if we want to know that expectation, we need to know what the joint distribution is, or the conditional distribution of the B's. And so by Bayes' rule, I'm just applying Bayes' rule, and I have this. And so there's a few terms in here. So this term here is the likelihood. And so that's saying what's going to be the distribution of the GWAS coefficients if we actually knew what the true effect sizes were. And so that's kind of simple. We know a lot about that. That's going to be just a correction because these GWASs are capturing some of the LD. And it's also going to account for the fact that there's some estimation error. So this one's not very hard. This guy here is the prior. And we don't really know what that is. And we're going to just have to make a choice about that. LD pred chooses to do a spike and slab distribution. I'll explain that in a second. This denominator term, though, is kind of tricky. And so as a result, we're not going to be able to get a closed form for this. But so we're going to have to find alternate ways to get it. But let's talk about the prior next. So if B corresponds to standardized genotypes, then what LD pred does is they assume a spike and slab prior, which means that there's some probability pi that the SNP is exactly null. That the effect of the SNP is not associated at all with the phenotype we're interested in. And then if it is associated with the phenotype, the effect sizes are drawn from a normal distribution. Yep.
If I understand correctly, do you use the weighted curve adapted data, or do you not?
So this one is not going to use any Winner's curse adjustments. It's going to kind of do this all internally. It's saying, given what we observe the beta GWAS to be, what do we think the beta hats are? Because remember, this looks actually a little bit like the Winner's curse adjustment. And in fact, when we do the Winner's curse adjustment, we're doing roughly the same thing, except we don't, the one that I showed you, we don't do any sort of accounting for the LD.
And aren't you afraid that adding this prior gives you an over-adjustment bias?
In what sense?
That you're shrinking your beta towards zero with zero prior?
So, well, the question is that an over-adjustment or not? We are shrinking things towards zero. So what's going to happen when we have this mass here at zero is that things that are estimated to have kind of a small effect, we're going to shrink a lot. And things that have a kind of large effect, we're going to shrink less. Yeah. If our assumption about the prior is the true distribution, that's actually going to be like the optimal, that's going to be the right choice. If we assume that there's this mass at zero and there's no mass at zero, then perhaps we'd be over-shrinking. That's a misspecification problem and not... I think that this world seems pretty reasonable, right? We don't think that... We don't think that every single SNP in the whole world affects the phenotype that we want. We have claimed all week, right, or all last week, that a lot of traits are very polygenic, and so a lot of SNPs are going to be affecting the outcome. But I don't think that we actually think that every single SNP does.
There's a new paper that's that just came out with the bioarchive, which is the omnigenic effects. I think it's kind of remains to be seen, but people are arguing that.
Oh, and actually I've heard people claim that. So even to the degree that this isn't true, what we could say is that maybe there's some mass of SNPs that have just a tiny, tiny, tiny effect. And then everything else of consequence is drawn from this normal distribution. And so that's going to be well approximated by this as well. So even in that case where we don't think that there is any SNP that actually affects it, this still could likely do better. Yes? Is pi a vector here, or is it just pi is just a single, it's bold, but it should be a single value. In this particular case, because it's, true or not, right? You could make it a vector if you wanted to talk about different types of SNPs having different pi's, but okay, great. So like I said, this thing is actually hard to evaluate, this denominator, and therefore this expectation. And so we're going to use numerical methods, the Markov chain, Monte Carlos, to get us to what this is. This means that LD pred doesn't run incredibly quickly. I think it takes about 2 hours to run. But after 2 hours, then we'll be able to, we'll have scores that take advantage of all these things that we're worried about.
You were going to say something about the denominator?
Yeah. So just the sense that, I said that this term is easy. This term we make an assumption. This term is hard. It's the denominator that makes this very hard to evaluate for just kind of any arbitrary for any arbitrary prior, or for this particular prior especially. And so that's why we have to resort to these numerical methods to get our weights.
Andrew, I think you once showed me that with pi equals to 0, you get a closed form solution, and I think for some of our phenotypes we found that LD Pred score does pretty much as well as any other LD Pred score. So sometimes that might be the way to go if you're worried about it.
That's true. Yeah. So if you think that pi is approximately 0, then you could just say that, okay, I think that the effects are just drawn from a normal distribution. That's going to be roughly equivalent to actually Kojo. It's going to be Kojo times a constant. And as a result, the polygenic score is going to be exactly the same in terms of its predictive power. So that's a way to speed this up a lot. Mm-hmm.
So here, basically, like when we have the stats, you would run LD Pred on each stat independently, then meta-analyze, and then construct the polygenic score, or?
So what you do is you would take your set of summary stats that are like, you can download them off the internet. And so you just have kind of one set of summary stats, and you pass all of those into LD Pred. And then LD Pred will do all of this machinery, and it will produce a weight for each SNP that's this object here. And then you could use those weights in your own data set to create a score.
And you'll do this in the problem set?
Yeah, you're gonna be doing this in the problem set. There's going to be a TA session this afternoon about it. You're going to become expert. And then you're going to do it in your own research, so you'll be even more expert. Okay. So let's talk about, I've been saying that this is what a polygenic score is theoretically. So why might we care? What are some ways that we might use a polygenic score? So first, we may just be interested in knowing how this score is associated with whatever it is that we're interested in. So there's a ton of papers. I think there's one more line after this one. There's a ton of papers that have done this, where they show that the score is associated with measures of cognitive performance, SES. These are all very interesting papers. I think they're all on the reading list too. So you can kind of see examples of people who have used these scores just to see, like, what is this score associated with? What is it correlated with? In principle, a twin study could also do this. But what a score allows you to do is to take this out of just twin data. You can look at a cross-sectional kind of between family sample. It will rely on different assumptions than a twin study will. And so that's kind of a first thing. Another thing you'd do is maybe if you wanted to talk about the causal effect of genetic factors. And so the polygenic score, because this polygenic score is made of Snips, your polygenic score is going to be random conditional on your parents. And so if you had a within family sample, you could then look at the causal effect of the polygenic score if you had family fixed effects. You maybe would be interested in treatment effect heterogeneity. So you might want to know, are there people who are more affected by some policy or less affected by some policy based on their polygenic score? And so I have some work on this. Here's Jonathan Ice, who have a paper where they're looking at this as well. And so you could just interact your polygenic score with your policy variable and see if you can predict what group is going to be more responsive. This is something that I think is very important but really unsexy. So if you wanted to, let's say that you have some data set, like you're doing some experiment maybe, and you have genetic data on these individuals. Now, even if the question you're asking has nothing to do with genetics, you could just throw in the polygenic score as a control, and it's going to absorb some of the residual variation, and it's going to boost the power of your analysis. And so for example, in Rietveld, he did a calculation that if the polygenic score has an R squared of just 15%, then that power increase that you get is the same as increasing your sample size by 17%. And so this is a way to boost power. And this is especially important if you're doing like really expensive experiments. And so if each additional person in your experiment is like $10,000 to include, and you're doing some like massive kindergarten intervention or something like that, then genotyping someone and adding a control will make it a lot easier. You can reduce the sample size you need for your experiment to be well powered. And so I think this is a concept that is really important. And in addition, if we have our genetic data and we have a bunch of weights for different phenotypes, we could create a polygenic score for education, and one for BMI, and one for risk preferences, or whatever outcomes we want. We could actually have several polygenic scores that we control for. Yep.
So in the previous slide, we were worried about basically the bias because we basically we were not accounting for all controls at the same time. Right? What if I have just a subset of the Snips that you use to actually construct the original polygenic score? So now let's say I cannot construct a polygenic score using everything, but just a subsample.
Yeah,
so
yeah.
Therefore, coming like the loss of the information that you have there using negative spot disclosure or something?
I mean, okay, so I think that you can't like get any information back that's totally lost. I mean, it may be that in your subset, some of the SNPs that you've lost are tagged by ones that are included. In which case, what you'd want to do is take this GWAS summary statistics for the set of SNPs that are in your data, and then pass that into LD-Pred. And that way, you're going to get the betas that are appropriate for the set of SNPs that you're using in your score. But there will be some information lost. If you don't have the SNPs, then you don't have them, I guess. Yes?
I have a question on the use of the terminology causal, because polygenic scores are constant over time. So even if we use a panel data and we put in this polygenic score, our conclusion will only be one of association rather than causality?
Yeah. So it depends on. Okay, so when we were saying causal at the beginning of the course, in terms of a single SNP, we had in our head this this thought experiment of like what would happen if you swapped out a single variant at conception, right? With these polygenic scores, that's not what we have exactly anymore. And then we said that our model, if you control for confounders like ancestry and things like that, then our betas do have this causal interpretation. When we restrict ourselves to our Bs, so I said we lost some SNPs, and so these are no longer causal. They do have we're only one step away from this causal interpretation at that point, where it's going to be confounded only by other SNPs that are not included in the genotype data set. Yeah,
I think you may have something in mind that's a little more complicated than.
Okay.
maybe this is
Go ahead, Dan.
So I think if you imagine this experiment where at conception we flip the genotypes for several variants in such a way that it changes the polygenic score, we could then ask, what is the ultimate outcome going to be in terms of the phenotype we're looking at? So now that's the experiment. We're changing several variants at once. Does that make sense? So it's still a hypothetical experiment where you're intervening at conception, but it's no longer just a single genotype.
Okay. Here we are. What is it? 1357?
Now there is one nuance that actually Patrick and I were talking about yesterday, and I think Patrick might be having in mind, which is maybe there's several different ways you could do that experiment to make the same change in the polygenic score. So I think the right way to think about this experiment is that it's the average effect over the different ways that you could do that hypothetical experiment.
Okay. Okay, so next you could use polygenic scores maybe as just a balance. This is kind of related to these control variables. Like we may have in mind a question that has nothing to do with genes, but we're just doing some experiment. And so in these experiments, we claim that we're randomized. So this could be either a true experiment, or this could be something like an RD setup where we have pseudo-random groups. And if we are truly randomized, then the distribution of our polygenic scores in the treatment and control group should be the same. And so, polygenic scores seem like ideal balance test variables for this because they're predetermined, and so it's just very clean. And so you can use you can compare the distribution and treatment and control, and if they're the same, then you're good. But if they're different, then maybe it means there's a problem with your randomization. This is kind of a, oh, go ahead.
Going back to the previous point, but then you should perhaps, if you already have the genetic data, instead look at the distribution of the genetic data directly, not in the distribution of the polygenic score. Right?
Yeah, I mean, the genetic data, though, is really high dimensional, right? So if you had the genetic data, you'd have to choose the subset of Snips that you were going to be testing. The polygenic score is just a nice composite measure.
Yeah, but let's say I can have a beta of 1 in one in the other, a beta equal to 1 in the other, but they may be completely different set of genes that are turned on and off, right?
Yeah. So, yeah, I mean, so I guess you could do any combination of these polygenic scores, or any combination of the Snips, or even just one Snip at a time. And in principle would be fine. I guess the thing I like about the polygenic scores is it seems like it's a nice, it's also interpretable. You can say that, the genetic factors that are associated with education seem to be balanced across these groups. And so if your experiment is about maybe education or something like that, then it seems like it's the more relevant thing. But you're right, the balance test, you could just use any individual Snip. In principle, that would be okay.
It's got to be really low powered for
An individual Snip?
Test every Snip you're running a GWAS of being assigned to the treatment group. So maybe that's the way to get like permutation-based correct p-values or something. So I'm not sure what else you would do with it.
Mm-hmm.
But one point about these use of controls, maybe you said this, Patrick, is that you can actually measure the polygenic score after the intervention, which is not true for most other types of controls.
Mm-hmm. Yeah, so what David was saying just now is a nice thing also about polygenic scores is, let's say that you ran your intervention, so you did like Perry preschool or something like that, and then 10 years later you still have access to your sample and you can go in and then genotype them. And the Snips, the genotypes that you measure 20 years later are still going to be the ones that applied back when they were children and the experiment was ran. And so that you could go and look at your data with this additional information later. Or if you have a polygenic score and you've gathered the genetic data, but the GWAS has been updated, you can also update your score at that point as well. So that's another kind of fun thing that you can do. Yes?
I was going to say another nice point too is if your data set doesn't have the phenotype that you want, you can still use the polygenic score. So for example, I mean, if you're looking at ADHD, not like the health and retirement study doesn't have that, but we have the polygenic score for it, so you can use that as a control or put it in your
Yeah, that's true. And so it's a way to sort of attempt to control for things that are maybe not even measured in your data set.
Jonathan will talk about a paper that does exactly that later this week.
Yeah. Mm-hmm. Great. And so this is something that's kind of more long range, something we may be able to do someday with polygenic scores. But let's say that we do a big GWAS of something like dyslexia, and we're able to predict a lot of the variation in something like that. Dyslexia, there's large advantages to catching it early and intervening early. And so with a polygenic score, that might help us identify people who are at risk, and so will help us catch these cases early and intervene earlier. So that's another thing that polygenic scores could be useful for in the future. There's a few limitations to polygenic scores. So I've been talking about how wonderful these things are. They're great. They're super powerful. They, we can apply them after our data's all been used. But the big problem is that we don't necessarily understand the mechanism. So before, we had a single Snip, and we say, oh, the Snip's associated with it. Let's look up our biological annotation tables, and we see it's on this gene, and we see that this gene is associated with whether or not mice give up in their mazes, and so we can maybe start thinking about I can start getting a good guess about what this Snip does. With this score, because it's a weighted sum of every Snip in the genome, there might be a lot of different pathways and a lot of different mechanisms at work. And so it's really hard to say this is what this score is doing. We can I mean, it goes back, I think, to your comment about can we say things about causality? I guess it's related in the sense that we don't really know. It's more about pathways, though. We don't really know what the pathways are, and there may be a bunch of different pathways acting at once. As a result, using it as a structural parameter is sometimes difficult to justify, because I might have the cognitive performance score, and we say, okay, this is this is IQ, or like, okay, let's say we have the education score, and we want to claim that this is all about IQ. Well, it might be that the education score is acting through other things as well, and so you need to be careful about that. Also, instrumental variables. So if you want to do an instrumental variables analysis with a polygenic score, that's also a little tricky because we know it starts with the gene, and we see that it's associated with the outcome, but it may be going through any number of pathways to get there. And so it's really hard to justify the exclusion restriction if you're using a polygenic score. It's just too many moving parts.
Jonathan's going to explain. If you don't know what instrumental variables is, Jonathan's going to explain it in a couple of days. So don't worry if that point didn't make sense.
It'll all become crystal clear. But there is some trade-off, right? If you have a polygenic score, you're going to have a lot more predictive power. So that's great. On the other hand, we don't really know what it's doing, so that's hard. Something that might cause this problem to not be as big is in the future we may be able to create polygenic scores that are just based on certain types of Snips. So we could say, I'm going to create a score that is only Snips that are involved in these biological mechanisms. Or I'm going to only use Snips that are, whatever question that we're interested in. And that can help us narrow these polygenic scores because we'll understand a little bit more what they're doing. But if we do that, then we're losing power, right? Because we're using a smaller set of Snips. And so currently, I don't think that these things are very easy yet. But as we get larger samples, I think stuff like this is going to be more feasible. Another issue is that we don't, we're creating these polygenic scores just for people of European ancestry. And as a result, these weights that we're doing are just going to apply for people of European ancestry. And in practice, so we have our educational attainment score, and it explains 7% of the variation in people of European ancestry. It only explains about 1% in people of African ancestry or people who are classified as Hispanics. And there's a few hypotheses as to why this might be. It could just be that people in these different groups have different causal effects. So the effect of a specific SNP is different in one group than another. What I think is the more likely problem, what contributes to most of this difference, is that there's differences in LD. And so you remember, our SNPs, because they're the Bs and not the betas, it's tagging SNPs that are not included in our data set to some degree. And that tagging is a function of the correlation between the sets of SNPs. And in different ancestry groups, that correlation is going to be different. And so the betas that we use that are estimated in an African or in a European sample may not be the right betas because it's not capturing tagging in the right way. And so we do even worse. And so I suspect that this is the bigger problem, although this is a very active area of research. People are still working on this. If we got larger and larger non-European samples, then we could, in principle, figure this out, or we could create scores that work in these different groups. And so again, that's something that's being worked on pretty actively as well.
So you're focused on the difference in the predictive power based on the actual underlying genetic factors, right? But part of this could be driven also by differences in environmental conditions between the groups.
Yeah. So I would characterize that as differences in the betas. Because if there's different environments, what that means is that the effect of swapping the allele in that group, it's going to pass through these environmental factors, and that's what gives us what the beta is. But yeah, so I would characterize the different environmental factors, which changes what the effect of the SNP is on the outcome. I would call that this. Did you have a question too, Chris?
Yeah, so we sort of calculated these B's in part using the D matrix for LD.
Mm-hmm.
My question is, so if you had LD for one of these groups, could you in principle apply LD for, say, an African ancestry sample and the betas from the cheapest from a European sample and get a better estimate?
Yeah, and so that's, I think, one of the main ways that people are approaching this problem. So like Alicia Martin is one of my colleagues at Broad, and so she's thinking a lot about this and how you would go about kind of correcting into B space and then back into the or beta space, I guess, and then back into this B space for people of different ancestry groups. So yeah, I think that's a reasonable thing, and this is kind of the sort of thing that people are working on.
So Patrick, for the first of those, that effects differ, have people looked at that using GREML or LD regression from one ethnicity to the other?
So LD regression is hard to do across ancestry groups because the LD scores differ across ancestry groups.
I mean, in principle, you could estimate a genetic correlation with GREML, right?
Haven't you done something like that?
We did it with schizophrenia.
Yeah. So it's like I think I've seen it before, but I think it's I mean, I don't know that literature incredibly well, but I guess you do.
I don't actually. I kind of haven't looked into it since then. But.
Yeah. So I mean, I think people are taking a lot of different. I mean, what that would do is would tell you whether or not this is likely. So if you take the genetic correlation or the correlation of these betas between ancestry groups using something like GREML, or I call it GREML, then if it's equal to 1, then it means that these betas are the same. But if it's different than 1, then it means that maybe this explanation is what's carrying a lot of the weight. Okay. So we've already talked a little bit about our polygenic scores. So we have this Snip Heritability, which is the maximum variation that could be explained by our polygenic scores. The question, but our polygenic scores don't do as well because of this attenuation bias. And it turns out that it's you can calculate how much worse you anticipate doing. And so, so we want to know how much worse are we going to do for a certain sample size. And so there's this paper here by Detweiler and colleagues that work out this formula. So in order to make this easier, we're going to have to make two assumptions. So first we're going to I actually don't think we need this assumption now that I'm looking at it harder. But we'll watch for this throughout the whole thing. Let me know if you see this assumption as we go through, but I don't actually think we need this. But we do need to assume that we have a set of independent SNPs. And so we're going to calculate this under the assumption that we're making our score with a bunch of independent things.
Just like we were doing the pruning thing.
So it's as if we had done pruning. So we prune before the GWAS.
Now we want to know.
And now we want to know how is this going to compare to the maximum amount of heritability that we could have here. Okay, so consider a regression of, this is our phenotype, onto our polygenic score. So this is the estimated polygenic score, not the true thing. So the coefficient of this regression, we're going to say is theta. And so the coefficient of that regression as basic OLS is going to be the covariance between the score and the phenotype divided by the variance of the score. So this means that the R squared that we'd expect to get from this regression is going to be the variance of the the coefficient times the score. So this is kind of the linear part of this regression, divided by the total variance in the phenotype. So by the properties of variance, we can just take this guy out and square it. And so now we're just left with theta squared over the variance of this thing divided by the variance of that thing. So then I can substitute our theta in. All right, so that's all I've done here. So notice that we have in the denominator here variance of a hat, and we have in the numerator here variance of a hat. So we can cancel one of these and this guy. What we're also going to do is, there should be a tilde here. But yeah, so this covariance term that we have in the numerator, well, y we've said is equal to the SNP additive genetic factor from the SNP plus the residual. So there's some amount not captured by our SNPs. And the additive genetic factor is the true additive genetic factor plus the noise. We worked that out several slides ago. And the residual here is going to be independent of both of these things here, because we're assuming that this is we're assuming that the polygenic score is estimated in a different sample, and so the residual in this sample will be independent of the error in the prediction sample, and so we'll be able to just cancel those out. So then the covariance here is equal to the covariance of just these true genetic factors. And so that's just the variance of a SNP. Okay, so that gets us to here. So let me point out what's happening. So we said that this covariance is equal to the variance of the true factor. So I'm going to take, it's squared, so I'm going to take one of them and put it over here. And I'm going to keep one of them here. And these ones canceled out, and so that gives us this expression. So this is just the Snip heritability. We did this before. It's the variance in the additive factor divided by the total variance. And so we have that there. And so now we need to know what these things are. So the variance of this is the variance of the polygenic score. We can just substitute in that we had before. And then because those are independent, the variance of the sum is the sum of the variance. Yeah, so that's what this thing here. So now we need to know what's the variance of the error. That's kind of the last piece, because we kind of have a sense of what this thing is, but we know there's some error. We don't necessarily know how much that is. So we can work that out. Well, substitute this expression in from before. So because now this is the part where we've assumed that the x's are independent. So because the x's are independent, the variance of the sum is equal to the sum of the variance. This is property of variance. And because the genotype, so this thing here is the estimation error, right? This is the estimated effect, and this is the true effect, and so the difference is how much error there is. Yep?
So, I think for that step, do we need the independence of the betas also?
Well, see, this is why I was saying I don't think that so if we just assume the betas are fixed and not random, all of this goes through. That's why I don't think we need that.
Okay, so you just want to treat them as fixed effects.
Yeah, yeah. So throughout, I'm going to treat them as just, these are the true things. They're not random variables.
Okay, but we're going to have a variance of that coming in at the end, but I guess you're just going to think of that as the variation across.
Yeah, because this thing is random,
Yeah.
but this thing is not. And so there is variance still. Okay, so because the error is going to be independent of the genotype, we can separate this out. So it's the variance of this times the variance of that. And now also because we've assumed that all these things are identically distributed, the sum of the variance of all these things is just going to be equal to the number of these things times the variance of each of them. Right, so now we've gotten rid of the sum and just we multiply by k. Okay, so we're going to assume that we've standardized our y and our x to just make things a little simpler. So like I told you, this is just the estimation error, right? Beta minus beta, or beta hat minus beta. And we know what the sampling variance of OLS is. It's going to be equal to the variance of the residual over the sample size. There would also be a variance of the genotype, but we've assumed that we've standardized the genotype, so that's 1. But this is just the standard OLS formula. And then if we assume that each SNP is only explaining a tiny bit of the variance, then this thing is going to be equal to 1 minus a tiny little bit, 1 minus the amount of variation explained by the single SNP, which is going to be approximately 1. So the variance of this genetic factor, so our formula before was that the SNP heritability was this divided by this thing. And so we could multiply that across. And so now we have the variance of a SNP is h squared times the variance of that. And this is 1. And so this is the SNP heritability. So now I think we've calculated all of the different terms. The variance of this u term that we had in our polygenic score is k times the variance of the genotype. That's 1. And the variance of the error, which is k, it's on the previous slide. It's on that slide. Did I miss it?
Yeah, it's the top bullet point.
The top bullet point.
Variance of beta hat minus.
Oh, just where's the k though? The k's out here. Sorry. Yeah. So k, and then this is just 1 over n. So k over n. Okay. So then plugging this into here, variance of the score of the true score is heritability, and so we can plug that in here. And that shows up here as well. And the variance of u is k over n. And so now we have this formula here. It's pretty simple. Right? We've just plugged a lot of things in. And it's just a function of the SNP heritability the number of SNPs and the sample size used to estimate our betas. Yeah, that just says the same thing at the top there. So here's some nice properties of this, just as like a sanity check. So whenever you do one of these big long derivations and you want to make sure it's like, oh, does this seem reasonable? I always like saying, okay, what happens when things are 0 or infinity or whatever? So let's think about what happens as n gets very large. So if n gets really big, what's going to happen to this term? Yeah, it's going to go to 0, so we can just ignore it. And so now we have snip heritability over snip heritability, so this goes away. And all we're left with is the snip heritability. And so this is the claim I was making before. Before I claimed if you have a really large sample size, our score is going to converge, the r squared of the score is going to converge to the snip heritability. And so we have that here. So we made this assumption that the number of SNPs, like we assumed that all the SNPs were independent, right? And so that's kind of restrictive because I wanted to say, well, we want to use as many SNPs as possible. And so kind of a way around it that you can go is you could instead talk about the effective number of SNPs. And so it's going to be a number that accounts for the correlation that exists between them. And so there's been people who have done this calculation to figure out what the right k is for genome-wide data. And they calculate it's about 70,000. And so if you're doing your own calculations of what you think the predictive power of your polygenic score is going to be and use k of 70,000, that should be about right.
For common variance.
For common variance, yeah.
From how many SNPs again?
So, like about 1 to 10 million, it's all going to be at 70. Because as you add more SNPs, once you get past the million kind of common variance, you're not really getting very many more effective SNPs. Mm-hmm. Okay, so the other thing that I've sort of, kind of a practical issue, is that if we use this formula, we will often end up overestimating the predictive power. And the problem, and the reason that is because imagine, our GWAS data comes from meta-analyzing a bunch of different cohorts together. And let's say that there's just a little bit of heterogeneity in the betas because they're all coming from different environments or things like that. And so as a result, the causal effect of the SNP in some American sample may be a tiny bit different than a European sample, or the effect of the score of the SNP in an older sample may be a little bit different than the effect of the score in a younger sample. And so this is going to kind of attenuate all of our estimates, and as a result, we often do a little bit worse than what Detweiler suggests. So in education, we've worked it out, and even though I told you the Snip heritability was about 20%, these cohort heterogeneity problems seem to, like, you can think of it more as being an h-squared of about 15%. In principle, if you could account for this heterogeneity, so we've been thinking that if you use something like MTAG, which allows for a little bit of difference between the effect sizes across cohorts, you could maybe get this back up to the SNP heritability, but this is stuff that we're working on and thinking about still.
Do you know for sure it couldn't be genetic heterogeneity, just like subtle LD differences?
That's true too. So it could also be, so I claimed earlier that the reason that our score doesn't do well in a sample of African ancestry is because there's these LD differences that cause our scores to not be quite right. And then we also claimed earlier that if you just stick to people of European ancestry, that's usually not enough to account for the stratification in our samples, so the differences in LD. And so David's saying, well, maybe it also just has to do with, there's subtle differences in LD, which is attenuating us just a little bit. So if you try to look in an African ancestry sample, it'll attenuate it a lot because those differences in LD are substantial. Small differences in LD might lead to just a small amount of attenuation. I don't think that we've...
Because I think the giant people have the same problem in their height analyses and so I want to make of that. But if I can make one comment about the date-pooler formula, every now and then there's a paper on bioarchive making claims about prediction accuracy that are wildly optimistic compared to what this formula predicts. And invariably what's happened is that there was some screw up in the selection of the validation sample that induced overlap. So I wonder if we can go back to the step of the argument where you
used
imperfect overlap. Because one thing I've never quite like to me it's very counterintuitive just how big the how many upward biases your R square, even with a little bit of overlap.
Mm-hmm.
I mean, is there some? So maybe you want to say something about. What
Yeah,
you're
yeah.
doing.
So before I assumed that so this is the residual in your prediction sample. And this thing here is the error in your discovery sample. And so I said, well, if these are different samples, then these things are going to be uncorrelated, right? Because the error in your discovery sample is going to be related to the residual in the discovery sample. However, if there is some overlap between your prediction sample and your discovery sample, then these two things are all of a sudden going to be positively correlated, which means that everywhere, so that means in the numerator where we said, okay, well this covariance is equal to the variance, and we substituted that in here, this would actually be variance plus a thing. And so this is going to lead to overestimation. And it's kind of maybe a nice way to see, it's an overfitting problem, right? We're using the same data for prediction as we did for discovery.
I think that thing is just going to be covariance of UI plus covariance of sigma, or covariance of the epsilon snip, right?
Yeah.
This is, yeah, and so that's going to be some function of the overlap between the two samples.
Mm-hmm.
Yes.
Yeah. So the larger the overlap is, the bigger that thing's going to be.
There's a nice paper by Naomi Ray and
Right.
Peter Fisher and
Yeah.
Mike Goddard, and they actually calculate these numbers for overlap. It's a huge bias. Like it's
Isn't it
amazing. Even
counterintuitive?
for like a very relatively small amount of overlap, you can get a spuriously much higher predictive power of the polygenic score. So that's definitely something to look out for, because you see that mistake with disturbing frequency.
Mm-hmm. And the same thing's going to apply to replication, right? So let's say that you have your replication sample and you want to see, like, I did this GWAS, or I did my study with some polygenic score, and I'm going to take this into a replication sample. If you're not careful to make sure that your replication sample is independent of your discovery sample, then you're going to see these biases, and it's going to be much too large. It's going to look like you're doing a lot better than maybe you actually are. In fact, sometimes you'd expect a slope of 1, and you see like a slope of like 1.3, or things as large as that. Mm-hmm. Bernie?
So this means like you shouldn't use the cohort to compute your polygenic score that you're interested in.
That's exactly right.
But is there like any overlap? Like, is that something we know, that there are people who participate in both of these studies, and what can we do about that?
Yeah, so the first thing you should definitely do is, like, let's say that you want to do some analysis in the HRS, right? And there's a score. The first thing to check is, you can actually just look, is the HRS in here? And if they aren't in there, then you're maybe mostly okay. And I think that there's some effort to make these scores available. So like, so you,
ISO for score without HRS.
yeah. So like, you'd call ISU or send her an email and say, hey, ISU, I need an HRS score. Did I just volunteer ISU to do this for everyone here, and everyone who's watching on a? Yeah. Send her cookies or something. But yeah, so that's the first thing to do. But then there may still be an issue. Like let's say that some of the people, let's say that the score is based on 23andMe, right? We don't know who the people from 23andMe are, and they may be in the HRS. It's hard to tell exactly if there's a problem or not. So some of the things that you could do first is, like an LD score regression, remember how the intercept term I claimed was Raymond claimed, was a function of the overlap between the samples? So you could do something like run LD score regression on the GWAS for the, that you're making your score out of, and the GWAS of just your discovery sample. Problem is that's going to be kind of low powered, right? If your discovery sample is just a few hundred people, then you're not really going to be easily to detect that. I don't know what other kind of tricks you could do.
I think the problem, it is surprising how little overlap, but it's not like truly sporadic random overlap is going to lead to much of a bias, right? If it's really like on the order of like 1% or something, yeah, you might get a small bias, but it's not going to be something that's going to invalidate your conclusion.
Next year we should derive data with overlap and just see what I get a sense of it.
Yeah, that'd be fun.
Useful, yeah.
Mm-hmm. Yeah.
So that problem you're describing about
had their genomic data, you could find people that are the same people in the two data sets, but it's the problem that they're basically warehoused separately and can't really.
Yeah, because we claim that one of the great things about polygenic scores is that I could go on the giant website and download the summary statistics and make a score. And so if, in that case, I don't have the genetic data, I can't really do any checks in that case for.
I suppose, depending on how much data you did have, or even if you said the polygenic scores, I mean, what would the odds be of two random people having the exact same? I mean, if there's one polygenic score, obviously that could happen by chance. But if you had like several polygenic scores and you used them.
No, but the issue is the data used to get the GWAS coefficient. So we don't have polygenic scores for the individuals that contributed to the GWAS summary stats. All we have are the estimates.
You just have the overall.
Yeah.
How is it impossible to like get those people to talk to each other and work it out? Because
These are really large samples and large cohorts. I don't know. I think it's tricky. We don't always know. It's confidential information. In general, I think if you just do the check to make sure that the whole cohort doesn't exist inside wherever you're getting your summary stats, I think that's probably fine. Like if I saw that, I wouldn't be suspicious. And if you wanted to show at least some effort to address that, you could do like the LD score regression thing. But again, that's going to be kind of low powered, so you should understand that that's only helping a little bit. But you could do it. Yeah.
Is this also a problem if you are talking about predicting a cohort that's like related to your discovery?
Yeah, so this is the question I was going to ask next. So let's say that you have a family sample. So you have a bunch of twins. And because these twins are related, you don't want to, you want to split your sample so that you can have a discovery sample to make your score and a replication sample. And you think, well, an easy way to do this would be to just split it in half. And we're going to put one sibling in the discovery and one sibling in the replication, right? And this is going to make estimation easier because you won't have to account for correlation like within family stuff. We have a cross-family sample. So what's the problem with that, of having siblings to make the score and siblings to make the, and the other sibling to test the statistic?
They're the same.
Yeah. They're not. Yeah.
If they're twins, they're exactly the same.
If they're identical twins, yeah. But even if they're just siblings, then they're half the same, right? And so it is true that even related individuals are sort of a mild version of, of overlap with the exact same individuals. But again, I don't know of an easy way. Unless you have the situation where you think you're being like sneaky and splitting your sample this way, I don't.
The issue is not their identical genes; it's a covariance with you, and they're going to share some component of that.
Yeah.
If they were like randomly assigned to different families at birth, it would be fine. Just split it up. Like
Oh yeah. Mm-hmm. Yeah. So that's right. So the issue is the covariance of the. The problem is that the residual also includes genes too. So that's so. Mm-hmm. But yeah, general environmental correlation will cause problems. Okay, we happy? Mm-hmm.
But sorry, the realistic version of this is not the twins. It's like cousins, right? It's that
Oh.
you estimated in a UK population, like the UK Biobank, and then you apply to predict in ELSPAC. And even if there's no actual people in the two, they're probably some cousins.
Mm-hmm. Yeah, once you get to cousins, the relatedness is a lot smaller. But so you have to worry about for every 4 cousins, you need to worry about one actual overlapping person or something like that, right?
Well, it also depends on the amount of correlation with the environment. Maybe the cousins share less environmental covariance, and so there's actually less of a worry even with the same amount of genetic relatedness.
Mm-hmm.
These are the kinds of issues that you need to be thinking about.
Yeah.
I have a question along these same lines. So you're talking about this R squared as the predictive power of the polygenic score out of sample.
Yes.
Right? But the betas that come out of the GWAS are really averages of the genetic effect over all of the environments that the people in the sample
Mm-hmm.
have, right? So if the people outside the sample have very different environment than the people inside the sample, the predictive power of the polygenic score is not going to be the R squared that you estimate.
That's true.
This is really the internal.
Yeah, so that's going to be reflected in a couple different places. One of the places it will show up is like this term here So like one of the consequences of this is the heritability in your discovery sample may be different than the heritability of your replication sample. And so this term out here, if we had done this carefully, there's a nice paper by Ronald de Vlaming where he actually does work through these heterogeneity issues pretty carefully. But like this term would be the prediction sample heritability, and this guy would be the discovery sample heritability. And then if you actually want to think that it's not just differences in heritability, but there's differences in genetic correlation across cohorts, then that's also going to show up, the genetic correlations are going to show up here as well. But yes, that's a good point. So if you're predicting into a different sample, the relationship of the betas in one sample or the other is something that's relevant as well.
I think that might be a very interesting research. Like sometimes such differences raise interesting questions and opportunities for research.
Yeah, and Megan and Robbie, I think, are going to talk a little bit about some of these kinds of issues on Wednesday, I think. Okay, great. So the question is how, so I gave you this formula. I said this is a great formula. It tends to work like all right. So I just want to kind of show you how this works and how well this works in terms of real data. And so each of these points corresponds to a score that's based on different GWAS statistics that are built on samples of different size. And so down here, this is a study of educational attainment based on a sample of, how big is that, like 2,000 or something? 2,000 people. And so you can see with such a small n, the predictive power of the score is like nothing.
That was the point of the paper, by the way.
And that was the point of the paper.
To go see the intercept.
Yeah. But then as we increase sample size, we see that this is kind of going up. The same thing we see for BMI. In the most recent results that we have for the education data, we see that we're getting a polygenic score up here of just under 9%, and I think this is HRS.
This isn't quite the latest result.
This isn't quite, it's like second to latest. Detweiler would have guessed that we'd be right here. And this is Detweiler adjusting down for this issue that we think that there's imperfect RG between our cohorts. And so we see that Detweiler is not doing super poorly. Yeah?
This is like a small question, but when you say incremental R squared, do you mean the
Oh.
semi-partial? Do you mean the partial?
Yes, that's a good question. I think that Isu will probably talk more detail. But when I say incremental R squared, what we mean is we first start and we regress the phenotype on the set of, on all of our covariates, and we write down the R squared of that regression. And then we regress the phenotype on all of our covariates and the score, and we write down that R squared, and we take the difference between the two.
And this is a minimal set of covariates.
That's the partial
Yeah,
R
yeah.
squared.
That's not, however, what the R squared that's being reported, for example, in the giant height papers. What they do is they residualize on sex and age first, and then they calculate their squared correlation with the score. And it's just a convention. It's not that one is right and the other one's wrong.
Right.
For a trait like height can make a big difference,
Yeah.
though, because sex and age.
Yeah, so for education it
Right.
doesn't matter because sex and age explain a tiny share of variance. For a height it makes a huge difference to screen because sex and age explain something like 40% of the
Right.
variance.
So there you want to use the semi-partial.
I mean, or you just want to be clear about what you do. I don't think it really, I don't think any of them are right or wrong, but you should just be explicit about what approach you're using when you're reporting the R squared.
And obviously the methodology here is the same for the two traits.
Mm-hmm. So you might want to say, well, then let's project. So we think Detweiler is doing okay. What is the relationship between R squared and sample size? And so what I've done is I've taken the heritabilities that I showed you in the table before, and I'm plotting here what Detweiler suggests the R squared is going to be for different sample sizes. So notice that these are in scales of millions. And so at 1 million, we'd expect subjective well-being to have the polygenic score for subjective well-being to explain about 5%, education, about 15, height we'd expect to be to like 42, 43. And so as you get, the gains are really large for the first, 500,000, still pretty large to the first million. Once you get above 1 or 2 million, the amount of predictive power that you're going to get by adding additional samples starts to be kind of minimal. And in all cases, these curves are asymptoting at this maximum Snip heritability.
And where do we live right now in the parameter space on the x-axis?
Yeah, so for like education attainment, the numbers that we have right now are about 750,000. So we're about right here. This is higher than what we're, I think we're actually getting 11%, where this looks like we're closer to 15% based on this figure. And I think this just goes back again to this problem of, we're meta-analyzing across different cohorts, and the betas may not be exactly the same for all the cohorts, and so we're doing a little worse than what we see in this picture. Mm-hmm.
So it may be possible to actually do a little bit better than this picture for a few reasons. One is maybe we can adjust for the phenotype heterogeneity, like you mentioned before, using something like MTAG. And then there's also, this is just the common variance, and you could imagine incorporating some predictive power from rare variants and things we haven't talked about so far in this course. But there you could bump this up maybe a little bit more beyond.
Yeah, and bumping it up would be equivalent to is we're saying that the Snip heritability is 5% or 50% for height, but if we included a bunch of rare variants, and so the Snip heritability of that set of SNPs or that set of variants is like 60%, then this is just going to be stretched upward.
Another cool thing about this graph is that it kind of illustrates why it's an exciting time to be in this field. So, as little as 3-4 years ago, we were, for all intents and purposes, in the origin, and within a year we'll be at 1 million. Yeah.
So I started doing this work when we were living right here, and so it's kind of fun to be here now.
So the difference between, you're talking about like here was 9%, the next slide is like 11%. That's prediction versus just the discovery sample?
No, these are all prediction, but this isn't a smaller. So this is the actual observed prediction amount, accounting for the heterogeneity, and so so we get this point by assuming that the Snip heritability is 15%, but we think that we're using that 15% because we think that because we're analyzing across different cohorts, the heritability across cohorts is not quite the 20 that we can observe if we just estimate the Snip heritability directly.
But it's just like, why is that one 9% and the other one 11%?
But one's a theoretical projection.
Oh yes, so this is a theoretical projection. It's also just sample dependent too. This is HRS.
Pointed where we were at though, right? I guess, like, I've heard double digits, and then you're just saying 9%. That's what I'm asking.
Okay, so in the HRS, there's also a difference in sample too, right?
Yeah, so right now the ad health prediction has about 8,500 people in it, and the ad health prediction has about 5,000 people in it.
Oh no, but what's the R squared? And
R squared is 9.2 in HRS, 9.2 in HRS, and 10.8 in F.
Yeah, so that's also, there's some sampling variance in the R squared here.
Yeah, I think the answer to Sam's question is that we made the previous figure under a different assumption about h squared.
Mm-hmm.
So it depends on whether you calibrate the formula using the h squared matches some previous r squared or something else.
But it's also not clear if this is kind of too low or too high, and and then the 11% that I've been quoting that we also get, it's not clear if that's too low or too high. There's, but we're in the ballpark of 10.
That answer there just confused me a bit. I thought they were calculating those R squares here, or calculating. How are they?
So this point here is actually like we created a score, we predicted educational attainment in the HRS, and the incremental R squared is is 9.2 or whatever it is. The X is the theoretical, what the Detweiler formula would predict we would get, based on assumptions about what the heritability is, and so we to get this point, we assumed that the heritability was about 15. When I made this picture, I assumed it was 20 to match the table that I showed earlier in the slides.
So Patrick, how important is it that in the original GWAS, where you're getting the beta hats, that people are controlling for the same things across samples?
So it's if the things that you're controlling, so it depends on the things that you're talking about controlling for, right? If you're controlling for things that you think are going to be independent of the SNPs, so like sex or age, those things shouldn't affect the estimate in expectation, because they're independent of the SNP, and they're just going to absorb some of the residual variation and give you a more precise estimate. If you're controlling for things that are correlated with the SNP, then it's true, your betas then might be different in one cohort or the other, and so it's more important that you're controlling for the same things in your different cohorts in that case.
So
I'm not sure, but I think that what you get as the additional R squared, it's like really the partial R squared, right? So, which is basically how much of the variation in your phenotype that's unexplained by everything you control for can you explain uniquely, but what comes from the SNP, right? Or like
Or from the score.
Or from the score. But then, since in a sense we always have the environment kind of like left out of here, right? Which is kind of what my point was last week about the inclusion of the UK, why suddenly you may see a whole bunch of other things. But then your adjusted R square really depends on this. So making a big point about the predicted R square, isn't it kind of, I mean, of course here it may look like 0.5, but perhaps if I put the environment and control for it, it may go up, it may go down.
So if the environment is independent of your SNPs, so if you're choosing factors that are independent of your genotypes,
think about schooling system, for example, right?
okay, so if we think controlling for the schooling system. So again, yeah, if you believe that the genotype is independent of the schooling system, and so to say that, I'm abstracting to a world where there's like not cross cohort stratification, right? Then in that
imagine these are all people from German descent living in Texas, right?
Okay.
Different counties have different schooling systems. So again, how the gene will actually affect environment, educational attainment may depend on how the schooling is provided, for example. Right?
And that's perfectly, I mean, people have written such papers. That is a perfectly interesting way to use it.
No. I'm just saying, like, in the sense.
And it's a perfectly reasonable hypothesis for why you sometimes you do worse than the
Mhm.
projections. Yeah.
But you see that in a sense, these R squares are not something like objectively given out there independent of the environment. So
okay. Yeah. And so to make these, what we've assumed is that the betas in the prediction sample and the discovery sample are the same. So it's just going back to this, so we've made this strong assumption. If there's differences of environment, again, this is differences in beta, and if there's differences in beta, the formula here doesn't apply. But there is work that talks about, what you can expect if your betas are going to be different in either within the cohorts that you use to your GWAS or different between your discovery and your replication sample. So and we could do that, but this is just sort of a simple, just a nice first pass what we expect to see, with the understanding that we are making this assumption about the betas being the same. Yeah.
I got two questions, but the first one was just really quickly. So you were saying that things that were independent of the it's like cohorts that are independent of the SNPs, and you said sex. Do we not include anything on the sex chromosome?
You could, but it's not being done much these days.
Yeah. We usually just use these are called we call them the autosomes, and so we just do the autosomal non-sex chromosome.
And then in terms of like what we think the difference between like the blue line and then the dotted line is, just like the sort of what the observed R squared.
It's like this distance.
Yeah, sort of a priori heritability, Snip heritability. Like, and we think of these different things like temporal stuff, cohort stuff, like environmental things. Is there a way to tease apart, like, is there a way to figure out how much of it is due to just like differential LD in Europe, or like, and then versus like how much it is due to like Europe is just different than America? Yeah.
So again, this is kind of the frontier of a lot of the things that people are doing right now, trying to understand what these differences are. So I said we've made this assumption that the betas are all the same. Maybe they're not the same, and so people are saying how can we determine if they're different in the first place, and if they're systematically different in observable ways. And I think those are actually really interesting questions. If we see that the betas are tend to be the same across these pairs of groups, but tend to be different across like these pairs of these types of groups, then we can start thinking about those there's some sort of different like environmental difference or something like that that's causing our betas to be different, and you could then go from there to try to understand what's happening and what the mechanisms are that are explaining the variation in the score. Lauren, yeah.
Oh, sorry, I had a question about that. So Dan mentioned that there were cohorts where they were controlling for changes in the school system when they calculated the betas for the EA. So some of them are controlling for those environmental differences that might lead to changes in beta causal. But not all the cohorts are doing that.
Well, we asked all the cohorts to do it for any kind of change in the schooling system that happened during the sample period that was relevant for the estimation. So hopefully they're all doing it if it matters.
Okay.
Yeah, that's actually one more factor that one can consider when trying to understand departures from the projections. It's an open question to what extent like errors in meta-analysis contribute to this, because who knows what they really did, right? And we talked about all the things we can do to catch errors, but ultimately there are a bunch of things that could go wrong that are near impossible to detect, and it's a little bit hard to know for sure to what extent they're important.
And so theoretically, I mean, if we want to push up our R squared, we'd rather have increases in sample size coming from the same area,
Absolutely,
rather than lots of. I mean, I think that goes back to his question too. I mean, if I said to you, I can give you 500,000 more people, do you want them all to come from the same country, or 500,000 from 5 different countries?
So so it's going to be a function of the, so if we think that the RG in your new population is close to 1, so you think the betas are like, maybe they're not exactly the same, but they're close to the same, you're probably better off getting 500,000 new people with a slightly different beta, right? I mean, to the extent, I guess once we're right here or something like that, if the slightly different beta is going to lower the heritability to like down there, then I guess you're worse off. But in general, I think increasing your sample size, at the place where we're living right now, increasing your sample size is probably kind of first order beneficial relative to these small deviations in environmental factors that alter the betas a little bit. But it's an empirical question. The statement that I'm making is just like, in general, this seems to be true.